today let us analyze, find out ways if we can simplify the analysis of circuits that are weakly nonlinear, right. And as usual, so as usual, we will it makes sense to work with a simple example rather than to complicate our lives by drowning ourselves in notation. So, I am going to take a very simple example. Let us say our good old friend the first order RC network. Of course, if the resistance was linear, then all of you would laugh at it and say, there is nothing to do, right. Now, the question we are going to ask is what happens if the resistance is nonlinear. So, let us say this is V out and the conductance is basically let us say this is V 1 and V 2 and the current I for this conductance here is given by, so G times V 1 minus V 2 plus, let me call it G 1 times V 1 minus V 2 plus G 2 times V 1 minus V 2 the whole square plus G 3 times V 1 minus V 3 the whole cube, right. And we hope that we will be operating in a range that the higher order terms can be neglected, right. And the next thing we also hope is that weak nonlinearity holds. That basically means that the strength of these two terms is much smaller than the strength of the linear term, right. So, well, we know for sure that let us call this therefore, this is G of a function G. So, this current therefore would be G 1 times V o minus V I plus G 2 times V o minus V I the whole square plus G 3 times V o minus V I the whole cube, right. Well, the only thing we know is how to write Kirchhoff's laws. So, we will do that. So, the Kirchhoff's law is are telling us that C times dVo by dt plus G 1 times V o minus V I plus, no, not that, you have taken into account the entire current to the resistor, not merely the linear term, right, plus G 2 times V o minus V I the whole square plus G 3 times V o minus V I the whole cube must be equal to 0. So, this is nothing but KCL at the output node. Right. Now, one thing that I would like to point out is the following. If the resistor was perfectly linear, what would we have got? C dVo by dt plus G 1 times V o equals G 1 times V I, right, because the G 2 and the G 3 terms will be 0, right. One observation that I would like to draw your attention to is the following. If this the resistor was linear, what all do we notice here? This is what kind of differential equation? It is first order differential equation because there is one capacitor, but what else? What kind of differential equation is it? It is a linear differential equation, right. with Vi being the input, all right. Now, suppose Vi is increased to a number z, z is some number, right. It is not to be confused with the Z transform or anything, it is just simply a number. If I scale Vi by a number z, right, what comment can you make? Let us say when Vi was the input, let us say Vo was the output. Now, if I scale the input by a number z, what comment can we make about the output? Very simple, the output will also scale by a number, sorry, this must be z times V, all right. Now, based on our experience yesterday, when we looked at memoryless nonlinearities, we saw that whenever you have second order nonlinearity, apart from the fundamental, you have second harmonic term, which is basically arising because of something multiplying with itself. When you have third harmonic, when you have third order nonlinearity, you get something proportional to, the by itself twice. So, basically you get error terms which are proportional to the cube of the input amplitude. So, if you have second order nonlinearity, we saw a error at the output or whatever nonlinear terms which are proportional to the square of the input amplitude of the input signal. And likewise, if we have a cubic nonlinearity, they would also contain something which is proportional to the cube of the input amplitude, right. Now, let us bear that in mind. The next thing that I would like to draw your attention to is this fact here. This is of course a linear differential equation, as you have pointed out. What comment can we make about this equation? This is a nonlinear differential equation. Right, and in general nonlinear differential equations are difficult to solve. You might argue that here maybe we can, but more importantly, when you have a more complicated network, you now not only have nonlinear differential equations at every node, because the KCL KVL equations now become nonlinear differential equations, and they are all coupled, correct, because there is going to be Vi or whatever Vo of this node in one equation, then it is going to be appear in some other equation, right. And so, therefore, in general you will have coupled nonlinear differential equations, which might be virtually impossible to solve analytically, right. But if we know that we still haven't, of course, a general nonlinear differential equation is very difficult to solve, but what is it that we have not exploited yet? We understand that this is a nonlinear differential equation, and therefore it might be difficult to solve, but we have not exploited something that we know about the problem. And what is that?
Like output tones.
Can G2 and G3 be arbitrary?
G2, no, not. It will depend on the value, like those values will.
No. So, in other words, what I am asking you is, what aspect of the problem have we not used as yet? What information about the problem have we not used as yet?
They are like negligible compared to.
So, what we have not used is the fact that this part, we have not used the assumption of weak nonlinearity, right. So, therefore, we have not used the fact that these nonlinear components are much smaller than G1 into Vo minus Vo. Okay. So, that is one aspect. The next thing that I would like to draw your attention to is the following. So, when we saw when there was second order nonlinearity, right, in addition to the of course, the linear term. What did we see yesterday? If we increase the input amplitude by 1 dB, the within quotes the fundamental goes up by 1 dB, but the second harmonic goes up by 2 dB. So, in the 2 dB is coming because of the x square dependence on the input amplitude. So, therefore, using the same intuition, therefore, let us say our input here in the in the system was increased by a factor or was changed by a factor z, right. Okay. So, if that z was a very small number, in other words, if the input was multiplied by a number z, where that z is a very small number, then what terms do you think you can neglect, you can forget about in the to find the output?
That weakly nonlinear terms.
Yeah. So, if the input is tending to 0, then you can forget about the nonlinear terms, and you just use the linear differential equation, which you can solve easily, correct. Now, if the input is very small, in other words, if that z is very small, right, and you increase it by a factor of 2, what do you think will happen to the output?
Output will be 2 times of 20 log.
It will be, so if the input is very small, so that the weakly nonlinear terms can be neglected altogether, then if you increase the input by a factor of 2, the output will simply increase by that same factor 2, right. So, in other words, the output voltage VO of t, right, can be, so let us say, again let me copy and paste this. Let Vi be scaled by a number z, right. So, in other words, you replace Vi in the above equation with z times Vi, right, where z is simply a scalar, it is a number. So, okay. So, as z tends to 0, you can neglect and therefore, c times dVo by dt plus G1 times Vo is equal to G1 times Vi. G1 times, sorry, I should have Z here, times ZV. Does it make sense? Right. Now, as you keep increasing Z, what comment can you make about Vo? It is a linear differential equation. So, as Z is very small, if you keep increasing the input, if you increase input by, so the output Vo is proportional to Z. Okay. All right. Now, let us say Z starts becoming larger and larger, so that the nonlinear terms can no longer be neglected, right. So, based on our experience with second and third order nonlinearities, what comment can you make if you go on increasing the input amplitude due to second order nonlinearity? you should, apart from the linear term, you should also expect a component that is proportional to
like 2 times. Okay, that is the G2.
So, as you go on increasing z, where the weakly nonlinear terms can no longer be neglected, we saw with second order nonlinearity, we saw that apart from the fundamental, there is also a distortion term whose strength is proportional to
G2 A square.
yeah, G2 is okay, but more importantly, as you keep increasing the input amplitude, this the strength of that distortion term is proportional to the input amplitude squared.
Yeah, square term.
Do you understand that?
Yeah.
Right. So, if you go on increasing the input amplitude, input amplitude, therefore, the output must consist of a linear term, correct, something which is proportional to simply that Vi is constant, the only thing I am changing is I am changing Z, that the proportionality constant, right. So, so Vo of t therefore must contain a term which must be proportional to Z, because otherwise you will not get the linear term at all, right, and we will call that the VO1, right. Please notice that that 1 in the lower bracket basically indicates that it is proportional to Z power 1. Okay. All right. As you keep increasing Z, in other words, as the input amplitude goes on increasing, you will get, because there is second order nonlinearity, you should expect to see
Output changing proportional to the G square.
you should expect to see the output changing with respect to Z square. So, you will have some other component which is proportional to
G over
okay, and because you have third order nonlinearity,
GQ.
Z cube. All right. So, the question is, so this is basically a hunch based on our experience with distortion currents or distortion components in second and third order nonlinearities. All right. So, in other words, the intuition is the following: when for a given Vi, if Z is very small, right, then the output will simply grow in proportional to Z if Z is very small, and that makes intuitive sense, because if Z is very small, the Z square and Z cube and all these things become very small in relation to Z. As you keep increasing Z, right, the nonlinear terms start to affect the output, right. Because of second order nonlinearity, you should expect to see an error term which is proportional to Z square. You should also expect to see a term which is proportional to Z cube and all other higher order nonlinearities, right. So, now our question is, and this is consistent with what we observed yesterday, right. When we put in a fundamental into a second order into an amplifier with a second order nonlinearity, you get a fundamental term which is proportional to Z. You get a second order term, right, which is proportional to Z square, right. Okay, because remember, and this has got nothing to do with, don't get confused as to, don't think that the error only needs to be at the second harmonic, right. For example, when we saw gain compression in a third order amplifier, in an amplifier with third order nonlinearity, we saw that the fundamental also gets affected by a gain compression term. That gain compression term is proportional to A cube, correct. So, So, in other words, if you put in an input sine wave, it does not mean that V02 and V03 etc. only consist of second and third harmonics. They can consist of they can consist of even the input tone. You understand, right? It is just that V02 simply quantifies that error which scales as z square, and VO3 I mean that basically is quantifies the error that scales as z cube. All right. So, now the question is how do you find V01, V02 and V03 and all these higher order terms.